I will show you later on also some experimental results, but just as a basis for calculations, we are not going into details for experiments. So numerical methods are in our focus, and it was known for a long time now, couple of decades, that finite element method can be used not only for static calculations, but also for dynamic ones, and also for fatigue crack growth. But before Belichko and his co-workers introduced extended version of the finite element method, it was too complicated to do it. So I will focus my presentation of exactly what he introduced, and not what's now. I don't see any. Okay. Yes, I think it looks like. So it was not shared. Okay. Always troubles with online presentations. I'm not saying that XFEM is nowadays the only way to analyze and estimate fatigue crack growth. In the meantime, there were some other options as well, quite good, but I'm still considering, at least for today, this one. So I will say a few words about its finally mathematical essence. So XFEM actually uses so-called enhancement functions as a means of displaying all forms of discontinuous behavior, namely crack, of course. So it is a partly analytical solution for certain number of elements, for those that are either at the crack faces already or in front of crack. Actually, that enabled simple use of the method with, of course, some other details like dividing, that we have to, of course, to know which elements will be active during this process. So this is how we can do that in mathematical terms, and this illustrates well what I'm trying to point out. A crack is going through the mesh, and we have to treat, of course, these elements that are active in that process, but we are not adapting a mesh to a crack growth. And that was the most important improvement, and that is why we still use XFEM. And as I already emphasized, there are now also efficient methods to remesh during each crack step, but that's for somebody else to say about. Abacus was, as far as I know, the first to build in this method out of commercial softwares, of course. Also, ANSYS is frequently used. And as for the elements that are at our disposal, you can see that they are not only two-dimensional, but also three-dimensional. And my presentation today is focused on three-dimensional problems. Key point in this simulation is so-called Morpheo as a post-processing of Abacus results. Morpheo is actually in charge of calculating stress intensity factors in 3D, their distribution, and according to that, to predict crack path, and then to provide all data needed for Abacus for the next step of calculation. So let us see now two examples, and then we will certainly have a better idea what I'm talking about. The first one is about welded stringer panels, which are used in A380, and they are welded either by friction stir welding or by laser beam welding. In the case we are considering today here, it is laser beam welding. And you can see in this slide which parts of A380 are constructed using these stringer panels. Here you can see how that looks like, and also you can see a model or kind of specimen, but it's more than specimen, that we used to both test and then to numerically simulate. So there is a panel, straight one. It doesn't make much difference if it is a bit curved as in reality. And there are 4 stringers welded by laser beam welding in this case. And there is, of course, a crack. So such a model was used for experimental and then numerical investigation. Also, you can see the cross section of stringers and how they are welded. So this is more or less the same with some data that we used in numerical calculation. This is linear elastic analysis. So classical high cycle fatigue problem, Young modulus for aluminum alloy and Poisson ratio are given, and then Paris law coefficients, which are obtained experimentally. And all of data that we need is actually that. So for the numerical simulation, you can see now a model with boundary conditions, and you can see enlarged in the bottom to the right, finite element mesh, one of several that we have used. This one is the only one that had weld metal modeled as well. Other models were without it. That was just to trial and error and get the best mesh to simulate most realistically panel behavior. Now we started with kind of calibration. And that means we used a plain panel with a crack, 14 millimeters, for which we had also experimental results. So you can see at the bottom to the right that numerical results provided about 169 kilocycles, thousands, whereas experimental results indicated about 189, which is difference around 11%. One of the reasons for this difference is that Abacus and Morpheo typically provide a bit probably over conservative stress intensity factors. You can see in this comparison that NASGRO, which is another software that deals with the same problem, would estimate up to 10% less values of the stress intensity factor. This is important for later comparisons. And that also explains, in a way, previous difference. Anyhow, we decided not to do anything about it because our basic concept was that numerical simulation should provide conservative results. This is common engineering approach. This is what we also use for any engineering calculation. Our analytical expressions are always conservative and most of the time over-conservative. Now we have numerical solution, which is conservative, but still not over-conservative. Here you can see a couple of nice results of showing different steps for the mesh with 1 millimeter size elements. So after 68 step, crack reached the first to the left stiffener. Then after 78, you can see that it goes up and through the stiffener. And then after 138, it's both ways already in the next segment of a panel. And at 68, this calculation was over. We cannot always use this XFEM as we like. That is maybe important to know. We simply generate a mesh, we simulate the problem, and then we let Abacus and Orfeo do the calculations, but we still are not sure when it will stop and how good the approximations will be. So this is why we were playing with different meshes. The next two examples are for mesh with 2 millimeter size and mesh with 4 millimeter size, and you can see practically about the same, just a different number of cycles. So summarizing these results, we can see that 1 millimeter mesh, which is gray one, is far the most conservative, and all other models, finite element models, converged more or less to the same value of crack length and number of cycles. So the finest mesh is actually over conservative. If we compare these results with the experimental ones, then we can see that 290,000 cycles versus experimental data, which is 418, is not really the best that we could get out of this, but it is at least conservative, and we decided to keep it this way. There are a couple of possible explanations why this estimation is around 70% of the experimental results, but I will not go into details, at least by now. And yet the final calculation that we did was to estimate the number of cycles if we put additional welded clips, which are along the crack. And to somewhat surprisingly, this improved number of cycles just for 5%. And since this is quite complicated to make, our recommendation was not to do so. So stringers are okay, they improve a lot, as you can see here, the life, because from 169,000 it goes up to 290,000, but additional 5% increase by these welded clips, that's not recommendable. So we can also conclude here that XFEM can play a significant role because we may reduce to a minimum number of experiments, because at least if we were not quite satisfied with the results, but at least we could compare different geometries by using finite element method. Now, the second example, it is also from the aeronauticals. It is about wing spare. And this is now a very small plane, not that risky structure as the previous one. So here is the spar. It is practically I-beam, but it is made. It's also aluminum alloy, and it is traditionally made by riveting. Now, one of our tasks here was not only to simulate experimental results, but also to find out how much integral structure would be better. We were sure that integral structure is better, but it was necessary to quantify it. So experimental part of this research was done on kind of improvised equipment. You can see it. Here is our spar, and the results were quite interesting and realistic. You can see here spar after 58,000 cycles. First crack appeared here, it went this way and then this way. Also, at certain point, there was additional second crack in this part of the spar. Now, numerical simulation is done on the model, which is relatively simple. It's practically consola. And there was 1 millimeter crack introduced here at the location which was practically in all of 10 spars that we used. So this is the crack. I will speed up a bit. This is how it grows. And then after reaching this critical point, a crack in a numerical modeling went this way, contrary to the experimental one. So on the other hand side, number of cycles was surprisingly similar, but we didn't rush into conclusion that this is fantastic simulation, because first of all, crack went different way, but anyhow, we concluded that experimental crack growth for such a structure is not really predictable. It depends on local material properties or defects. So at the end of the day, we were quite satisfied with this, and we decided to go on with a numerical simulation for the integral structure. So here we see how the integral structure looks like, and then crack growths. We assumed 2 of them because experiments showed like that. And you can see how this crack grew from different angles and different number of steps. So finally, the result is 350,000 cycles, which is about 7 times more. So integral structure is far better. And not only that, but we introduced a modified integral structure with double-decker solution, in a way, with double bottom cap of the spar. Few nice figures to show how it went all the way, and the final result, 2 million of cycles. So that is a phenomenal improvement, and by that I may conclude on time. So already discussed what is written in black, but more generally, we can definitely conclude that XFEM plays significant role in estimating fatigue life of integral structure, and not only that, but all kinds of structures. So we are not limited by geometry or type of structure, and I will just briefly run through a couple of different examples that we also simulated. These are orthopedic plates. This is artificial implant hip. This is pressure vessel with axial crack. This is a shaft in a hydropower plant. And finally, this is surface welded simulation of crack that eventually goes through it. So thank you. And just to quote Enrico Fermi, you can read it on your own.